Let's check out similarity in right triangles. For today's agenda, we're going to explore a theorem involving similar right triangles and then go over some examples. So here's the theorem. The altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original triangle and to each other. So in symbols, we get that triangle ABC is similar to triangle ACB and similar to triangle BDC. Let me show you why this is true. So take into consideration this right triangle below. We have triangle ABC and it's a right triangle because it has this square tick mark. And I'm going to label this triangle as 1. And keep in mind that this is the original copy. Now in geometry, an altitude of a triangle is a line segment through a vertex and is perpendicular to a line containing the base. So we can imagine this line segment being the altitude through this vertex B, and here we're using AC as our base. And what happens here is that we create two right triangles. That's what it means to be perpendicular. So here we create this right triangle, and here we create this, right angle and right angle right there. You can see that my original copy got split into two smaller triangles. That's where triangle 2 and triangle 3 come into play. And what this theorem is saying is that these two triangles are going to be similar. And not only are they going to be similar to each other, but they're going to be similar to the original triangle we had, which was the one I labeled as 1. So let's go ahead and prove this statement. We're going to do it informally. But here, what we want to do is position all of the triangles so that they're in the same orientation, or so they're facing the same side. They should all be facing in the same direction. So here I'm going to make a copy of my original triangle, and I'm going to make triangle 2 and triangle 3 be in the same orientation as triangle 1. So let's begin with triangle 2. Now I've extracted triangle 2 from this figure, and here we see that we want this triangle to be in the same orientation as triangle 1. So we're good with the A's are on the same position, but now notice that this 90-degree angle has to be on the top. So what I'm going to do here is I'm going to flip this triangle over, and here's what we're going to get. Once I flip it over, we're going to have this version of the triangle, triangle ADB, with D being the 90-degree angle. So let's go ahead and graph this triangle and put it next to triangle 1, because now they are facing the same direction, or you can say they're in the same orientation. We have to do the same thing for triangle 3 now. Here I've extracted triangle 3. And we have to do the same thing. We have to make sure that triangle 3 is in the same orientation as the original copy, which was triangle 1. So we're good with the right angle. The C is in the right place. But now notice that here D is the right angle, and it has to be here on the top. So for this one, we're going to have to flip it in that direction right there. And we're going to get this orientation of the triangle once we flip it over. So here we can adjust it quickly. So let's go ahead and grab this and make sure that it's oriented in the same way as triangle 1. And we have all 3 triangles in the same direction now. And let me go ahead and label this as 3. Now I'm going to show you that these 3 triangles are all similar to each other, beginning by analyzing triangle 1 and triangle 2. Now if you recall our lesson on similarity, or triangle similarity, you can see that triangle ABC is similar to triangle ADB, because we can use the angle similarity postulate by AA similarity postulate. Here these two triangles share the same angle of A, and they also share one 90-degree angle. That means that the two triangles are similar by the AA postulate, and moreover, since they're similar, we can claim that all corresponding angles have to be congruent, which then leads us to conclude that angle B and angle C, since they're corresponding angles, they have to be congruent. So angle B is also with two tick marks. Next, I can claim that triangle ABC, the original, is similar to triangle BDC by the same thing, by the AA similarity postulate. Because again, you can see that they both share angle C, and then they both share a 90-degree angle. So if two angles of a triangle are congruent to two angles of another triangle, then by the AA similarity postulate, these two triangles are similar. And for similar figures, corresponding angles have to be congruent, which means that angle A is congruent to angle B, so B also has one tick mark. Finally, I claim that triangle ADB, triangle 2, is similar to triangle BDC, the third triangle, and again by the AA similarity postulate. Here we have more than two angles, right? B is congruent to A, B is congruent to C, and we have that 90-degree angle right here. And now you can see how each one of these triangles is congruent to one another, which is exactly what this theorem states. And I'm really sorry, I apologize, but I made a little tiny typo here. So it should say ADB. I think I had it backwards. And hence we've proved the theorem. So now let's check out some examples and apply it and see how we're gonna figure out problems with this statement. And before we move on, something that I was absent-minded about is that here, when we dissected a B, we actually created two different angles, B1 and B2. So here, this one should really be B1 and this one should be B2. The original one is the actual B, which is the sum of these two. But nevertheless, the important part is that these three triangles are similar. So let's go ahead and jump into some examples.